So let us recall transitive action of a group. So action of a group G on some set A is called transitive if for any two elements, say A1 and A2, lying in the set A, there exists an element G in the group G such that this A1 is equal to GA2. So that is, you can connect this A1 and A2 via this element G. So in other words, all elements of set A lie in one orbit. So standard example is the symmetric group Sn. This acts on the permutation. This acts as a permutation on the set of integers 1, 2, 3, 4 all the way to n. So this is the same way the Galois group will permute the roots of irreducible polynomial. So again, recall our fundamental theorem that K over F is a Galois extension if and only if K is splitting field of some separable polynomial F which lies over this field F. So let us start with the separable polynomial, and then we will show the transitive action of the Galois group on the roots of this separable polynomial. So say you have the separable polynomial and it has these roots alpha 1, alpha 2 all the way to alpha d. So now your splitting field is nothing but your base field F. So say this F lies in this F, your base field F, and you adjoin all the roots. You take all the roots, you have adjoined it. And now you know the Galois group is this group of automorphisms of K which fix F. So same as what I'm writing right here. So this is group of automorphisms of K which fixes F, where K is just F adjoined with all the roots of our separable polynomial. So this Galois group, this is determined by the permutation of the roots. So notice that again you have this K here, this K is precisely this, and we are keeping this F fixed in the automorphisms. So automorphisms of K which keep F fixed. So if this F is fixed, only thing you are permuting are these roots. So after all, you have constructed the splitting fields by adjoining roots to F, and since F is just fixed, you can only permute these roots. So we obviously have an injection. You know, our Galois group, this we are writing as G subscript F, this GF, which is automorphisms of K which fix F. This injects into this symmetric group. So that is a group of permutations of integers. So say every integer corresponds to one of these roots. So 1 corresponds to here, alpha 2 corresponds to 2, and say d corresponds to this. So permuting these roots is same as, you know, applying this permutation on these integers 1 to d. So for example, we saw in example 3 that x4 minus 2, this had a Galois group which was d8. So this we said lied over rationals, and Galois group was d8, and this dihedral group of order 8, this injects into S4. There were 4 roots. So this was our example 3. So this transitive action of the Galois group on the roots can determine irreducibility of a polynomial. So you have a polynomial f over f. It is irreducible if and only if its corresponding Galois group acts transitively on the roots of f. So that is, it permutes all the roots of f. So that is theta of gf is a subgroup of s of t. So this dihedral group of order 8 is a subgroup of s of 4, and this we saw permuted all the roots of our polynomial x4 minus 2 which lied over rationals. So therefore x4 minus 2 is irreducible. So let us start here. So first assume that f is reducible. So you write f is equal to g times h, with where degree of g and degree of h is both greater than 0. So say g is irreducible. So then say you have root alpha of g. Now if you apply the Galois group onto it, the coefficients of g will be there fixed, but its root would be permuted to sigma alpha, and this would be, as we have seen before, the Galois group permutes the root, so the sigma alpha will be other root of g. So the roots of g are kind of isolated from roots of h. So this Galois group here will permute only roots of g, and it will not interact with the roots of h. So we can see the action is not transitive because you cannot connect roots of h to roots of g via the Galois group. So we have proved here not irreducible implies not transitive. And now you take contrapositive of this. So contrapositive would say that transitive implies irreducible. So this direction is done. Now we have to go in the other direction. So say if f is irreducible, and say you have take its two roots, alpha 1 and alpha j. So then you have f of alpha 1 is this iso to f of alpha j. So this we know, you know that f of x, you modulo out our irreducible polynomial. This is iso to f of alpha I, and this is iso to f of alpha j. And the isomorphism is precisely permuting the roots alpha I and alpha j. So you can permute these roots. So this iso comes from permuting these roots because the coefficients are exactly the same. So now we want to extend this permutation all the way to the Galois group, so that we can say that irreducibility implies transitivity. So this direction we want to show. So you know that two roots you can permute, you want to be able to extend it to all the roots. So first recall that we had proved this big result, uniqueness of splitting fields. So by this big result, uniqueness of splitting fields, we can extend this particular isomorphism to isomorphism of our splitting fields. So notice that our splitting field is precisely this right here, which is k. This is a splitting field. That basically means that you just take two roots, your permutation is determined by this, and this you carry out to here. So the permutation here you carry out in here also to automorphisms of our splitting field k, which is f adjoining all the roots to it over f. So therefore you are done. So whatever automorphism is here, you have been able to carry it to the splitting field automorphism, and this automorphisms of k over f is precisely the Galois group. So if you have given irreducibility, then you can go to transitivity. You can connect any two roots because you can extend this isomorphism by uniqueness of splitting fields. So degree 2 and degree 3 are easy to describe. So say you have degree 2, say f is irreducible, then its only non-trivial injections into S2 would be S2. So S2 is just a cyclic group of order 2, which is nothing but z modulo out 2z. So cyclic group of order 2. And if it is reducible, then obviously it's degree 2 polynomial. That means it factors as a linear factor. So if it is linear, then obviously you have trivial Galois group. Because it's a linear factor, it already has the roots in there. So this is 1 if it is linear. So on the other hand, if you have degree 3 polynomial, if it is irreducible, then you have to consider that that the Galois group, as we seen here, the Galois group injects into symmetric group of order 3. So what are the non-trivial Galois groups? So the non-trivial Galois groups are either entire S3 itself, or it is the alternating group, the standard subgroup of symmetric group S3. So this is the alternating group. So this alternating group is same as cyclic group of order 3, which we are setting as Galois group. So if degree of f is 3 and it is irreducible, there are only two possibilities for the Galois group for f, S3 and A3. On the other hand, if f is reducible, then it has two possibilities again. It is reducible, that means it factors as degree 2 times degree 1. So if it is degree 2, you're back here. So if degree 2 polynomial is irreducible, then you have cyclic group of order 2, and degree 1 is linear, so just a trivial factor. So again, recall that cyclic group of order 2 is nothing but z over 2z, and cyclic group of order 3 is z over 3z. So let us do important examples. This we have already done before. So say you have this polynomial x square minus 2 times x square minus 3 over rationals. So notice that this is product of irreducible polynomials. So now you have the roots here, minus root 2 plus root 2 minus root 3 plus root 3. So this is how it will factorize. So this obviously factorization is over rationals. You adjoin root 2 and root 3 to it. So this is, say, the first root, this is the second root, this is the third root, and this is the fourth root. So first and second root are permuted, say, via permutation sigma, and third and fourth root are permuted via permutation tau. So set sigma as 1, 2, tau as 3, 4. So sigma tau would be like this. So now you can see this is disjoint. And that is precisely what we used in the proof right here. You know, this roots cannot be permuted throughout. This minus root 2 and plus root 2, they cannot be interchanged with minus root 3 and plus root 3. So this we had discussed before this example. So this example we had discussed before. And therefore you get the Galois group as just the sigma tau, which is a subgroup of S4. So obviously we were expecting, so maybe at the maximum all possible 4 roots permute, but you know, we get a subgroup. So this is a strict subgroup. So this example was covered in example 1 lecture. So lecture on example 1, this example was covered in detail. So another example, this was our example 2. So say x cube minus 2 over rationals. This is again irreducible, and it will factorize like this. So the 3 roots are 1, 2 and 3. So the sigma, it permutes all 3 roots, 1, 2 and 3. It permutes them, whereas tau, it just permutes the 2 complex roots. So these 2 complex roots are permuted. These are permuted by our tau. So tau is 2, 3. So we saw our Galois group is 1 sigma sigma square. This will permute all 3 roots, and then you have tau, tau sigma and tau sigma square. So this will give you S3. So that is permutation of all 3 roots. So now you can see that, you know, if you have an irreducible polynomial like this, you have permutation of all 3 roots S3. So that's what it is irreducible. Then our Galois group acts transitively. It permutes all the roots. So again, keep in mind this example also, x4 minus 2, it was irreducible, but our Galois group was not S4, it was D8, but still it is a subgroup of S4. So this D8 injects into S4, it is a subgroup. So this example also tells us that, you know, what is the possible size of the Galois group. So the maximum possible size of the Galois group is the size of the our permutation group. So Galois K over F, its maximum size is less than equal to D factorial, because this is the size of this group, symmetric group or permutation group.